Let's do a couple of examples that use some of the concepts that we've introduced in the past couple of parts of the lecture. The first, we're going to do one on normal strain, and it's going to look a little bit unusual because we're actually not going to use a straight line. A lot of the straight line examples that we could construct would be so trivial, we're not going to bother. So in this case, we're going to allow our normal strain to take a little bit different form, and we're going to take a rubber band that originally fits around a can that is 2 inches in diameter. So that's 2 inches, and that is a rubber band. And as you can tell, that's not going to be straight. It's got the shape of a circle, so it is curved. However, we can still use the same principle of normal strain. In this case, we would call it something like circumferential strain or circumferential normal strain. So it would actually have the subscript, if we cared about this, it would have an E theta theta if we use polar coordinates. So remember, in polar, that would be our R and that would be our theta. So in this case, we're really looking at the circumferential type of strain. But we're not going to really worry about that right now. What we're going to do is we're going to take that and make it fit over a can that is 2.01 inches diameter. So it's unstretched originally, and it barely fits around the can, and then we have to stretch it a little bit so that it fits around a can that is slightly larger. So that would be the deformed state. So in this case, even though it's not straight, we're going to go ahead and use then the same principle. So the normal strain, and again, what that means is change in length over length. Let's rewrite that. That would be the change in the length divided by the original. That's what we're after. So somebody has asked us, hey, what's that normal strain in that rubber band? And then find out what that's going to be. Well, remember then that the circumference of a circle is, a lot of us think about it as 2 pi r. But remember, 2r is the diameter, so it's also pi d. Now, I don't know about your education, but when I grew up, it was always 2 pi r. But that one has a little bit more resonance for us. And in fact, so frequently we're going to stick with the diameter of circular sections that one's actually a little bit easier to invoke. So what we would say is I would have pi times the d of the second state, the second diameter, minus the original length, which is pi times d1, all divided by the original length, which is pi times d1. So final length, final circumference, pi d2, minus the original, pi d1, all over pi d1. So that's just going to be, the pi's cancel out. We get 2.01 minus 2, all divided by 2. And that gives us a strain of epsilon is equal to 0.005. So 0.005. Now, at this point, that answer would be fine. And it would be positive. Notice it's growing. So we would do something like that just to reinforce it. And that would be a totally acceptable answer. However, frequently, what we will do is, and you'll see this sometimes, you'll say epsilon is equal to 0.005. And since we were using the dimensions of inches, then you would see people say it's inch per inch. That would also be okay. But there's another terminology tool that we will frequently use. And that is, people get tired of all these zeros after the decimal point. And what we're going to do is we're going to multiply this thing by 10 to the 6th. So that would be, I'm going to move the decimal point 1, 2, 3 to 5, and then 3 more, which would be 5,000. So I'm going to multiply it by 10 to the 6th, so that's 5,000. But then I have to multiply it by 10 to the minus 6, so I get back to 1. So 5,000 times 10 to the minus 6th. And that symbol, that suffix, has a label that we use frequently, and that is the symbol mu. So that's a Greek letter mu, And the word that we use for it is microstrain. And that is 10 to the minus sixth. So we would write then that epsilon is equal to 5,000 mu. And that is far more likely to be a number that you're going to see in any sort of analysis or any sort of engineering application. And we would say then that our strain is, so this is what we would say to one of our colleagues, 5,000 microstrain. So microstrain basically just means 10 to the minus sixth. And you'll get a chance to practice this, and you'll see this very, very frequently. And so it's a good concept. It's a good tool to practice using, so it just kind of rolls off of your tongue, because people, again, it's okay to say 0.005, but it's far more likely that if you're working with experimentalists, you will say 5,000 microstrain. So it's up to you then. So you would say, okay, that's 5,000. You got to do this in your head when you're first starting, times 10 to the minus 6. So you have to go 1, 2, 3, 4, 5, 6. So you could say, oh, 5,000 microstrain is 0.005. So it's a good chance for you to kind of get comfortable with that particular sort of concept. Now remember, it's positive because it's growing. And so that, and for this particular example, it's very, very simple. It's growing in size, so the strain is going to be positive. So once again, even though it is not straight, we can still use the idea of extension. So the length is growing, so it's okay to use that terminology. Now let's try an example with the shear strain. And we're going to make this really easy. If we've got a rectangular block, and it originally looked like this. So there was our solid in its old state. And that was 250 millimeters. Oh, I beg your pardon. That's going to be, 250 is right. So 250. And it is 500 millimeters in this direction. And let's go ahead and give it a coordinate direction. So that would be X, that would be Y. So there's our original. Now, by the way, you might be thinking, hey, that doesn't look very small. 500 millimeters is pretty big. We're going to put this under uniform strain. So we don't need to let the line element length go to 0, because the entire block is going to have the exact same deformation. So we put this under uniform deformation. And when we say uniform deformation, that means at every point in that domain, the strain is the same. So gamma is the same. There's not going to be any spatial variation with the shear strain. All right, so it was originally a rectangle like this, and then it somehow deformed into a shape that looks like this. It's going to move there. Then it's going to go up like this. Then it's going to go here. And then down here. There we go. And these distances, this corner moves up 0.38 millimeters. So obviously this is not to scale. And then the horizontal distance, this distance right here, is 0.2 millimeters. And then the upper section then moves accordingly. It also goes up that particular amount, so this point is moving up. But we don't really worry about that, because what we want, that's our point P, then we would like to have the shear strain at P. So what we would say is at P, we want gamma in the XY system. Now take a look at that before we do any numbers and see if you can figure out what is the sign going to be of gamma. Is that a positive shear strain or a negative shear strain? And if you need to, go ahead and pause the video and give it some thought. All right, if you're back, that's positive, because we put our thumb and our finger and we put it into the deformed position and there was no pain involved. We weren't spreading our thumb and our forefinger away. So we know that the answer is going to be a positive shear strain. Now remember, all of our deformations, in fact, let's write this up. So all our deformations are going to be small. Now again, when you see that word small, it is synonymous with infinitesimal. And that means that the angles are small also. So small angles also. So for example, when we did our original delta over L for our normal strain, if the bar is 12 inches long, we're not going to stretch it 6 inches. I mean, we're stretching a fraction of an inch because all of our deformations, all of our strains are going to be very, very small. And you can see that because in most structural systems, there's not much deformation. Every time you sit down in a chair, you don't see any deformation. It is very, very small. So in fact, let's put a box around that because that is a common assumption in all of our solids that we're going to be using. Now, if we introduce some sort of classroom example where we can see the deformation, that's pretty unusual. Most of the time we can't even see it, it's so small. All right, so if the angles are small, then notice what happens. We kind of set this up earlier. Then we've got this, the opposite over the adjacent. That's the one angle. And then we've also got this angle that adds in. So that's going to be this distance divided by this distance. So recall for small angles, what happens? Well, first off, remember sine of theta is approximately equal to theta. Tangent of theta is basically equal to theta. And the cosine of theta is basically equal to 1. So in this case, we're going to use this one. So what we would like is change in angle. That's this plus this. So that would be the tangent, pardon me, is going to be this over this. And then the tangent of this angle is going to be this over this. But since tangent is theta, we can just add those two. So remember, I'm going to shrink this down so you can see what they are. So I would say then that gamma xy is going to be 0.2. That's the opposite over the adjacent, so 250. Now in this case, we don't have to convert to meters because the units cancel out. It's millimeters upstairs, it's millimeters downstairs. And then we have plus 0.38, all divided by 500. So again, that's really the tangent, but the tangent is the angle, so we can get those things and add them together. And when we do that, we get 0.00156 radians. Or we could leave it off, it's dimensionless. But again, what we're going to do is 1, 2, 3, 4, 5, 6. So we're going to say or gamma xy is equal to plus 1560 microradians. And so we get to use it for the angle as well. So I went over 30 seconds. Actually, we're approaching a minute, so I'll owe you in the next lecture. And now we're done with part C.